Sometimes the solution to a problem really is as easy as it sounds. So this is find closest node to two given nodes, and it's a medium problem. So it says you are given a directed graph of n nodes numbered from 0 to n minus 1, where each node has at most one outgoing edge. The graph is represented by a given zero-index array edges of size n. So this is really helpful because you don't have to turn it into an adjacency matrix or anything. It already has the only connection for each node. So that's pretty nice of them. Indicating that there's a directed edge from node I to node edges of I. If there is no outgoing edge from I, then edges of I equals -1. So this is where the problem actually begins. You are given two integers, node 1 and node 2. And what it wants you to do is return the index of the node. So important, we're returning the actual index that can be reached from both node 1 and node 2, such that the maximum distance from node 1 to that node and from node 2 to that node is minimized. Okay, so that's pretty complicated, so let's try and clarify that. So in this example, you are given the option to start from node 1 and node 0, and we can see that both of these nodes connect to node 2 in one connection, and then from node 0, it also comes from one connection. And then it's the same for 3. You can connect to 3 in two jumps from node 1, and you connect to 3 from node 0 in 2 jumps. Now, this problem has that nasty Leetcode habit where some of the examples are way too simple to actually make the problem understandable. So I'm going to give a more complicated example with 9 nodes. So let's say in this example, it looks more like this. So we have 0 going to 4, 1 goes to 4, and then 2 goes to 8, and then 3 doesn't go anywhere. 4 goes to 9, and then 5 goes to 8, and then 6 goes to 4, and then 7 is going to go to 4 as well. 8 is going to go to 1, and then 9 is also going to go to 1. And in this example, node 1 is going to be equal 6. And then let's say that node 2, let's say that that's going to equal 2. Okay. So in this example, let's go ahead and change colors for you. In this example, from node 6, we can see that we can go to 4 in 1 jump, and then to 9 in 2 jumps, and then to 1 in 3 jumps. And then we would just go back to 4. So something to note is that cycles can exist in this problem. And then node 2, we start at node 2. We can get to node 8 in 1 jump, and then we can get to node 1 in 2 jumps, and then to node 4 in 3 jumps, and then we'll just have another loop so we can go here in 4. Okay, so then the question is, what is the maximum distance? What is the maximum between the distance from node 1 to some node and from node 2 to that same node? So in this example, there are only 3 nodes that all 3 of that both of the starting nodes can reach. That was node 1, node 4, and node 9. So the maximum between distance between both of their distances in node 1 is going to be what? It's going to be 3. And then the maximum between their 2 distances to node 4 is going to also be 3. And then their maximum between their 2 distances to 9 is going to be 4. So what's the answer? Because the maximum between their 2 distances of both node 1 and node 4 are both 3. Well, that's where it gives the last caveat, which is return the node with the smallest index, and if no possible answer exists, then return -1. So in this case, you would return 1 because 1 has the smaller index between node 1 and node 4. Okay, so let's take a look at step 2, brute force. How exactly would you solve this with brute force? Well, I guess you could start at every single node, and you could say follow the graph around and try to see where how long it takes you to end up at every node, right? So you could start at 2 and then go to 8, then go to 1, then to 4, then to 9, back to 1, realize you're in a loop. And then you could say look at node 1 and do the same thing in node 0. Graph problems tend to be difficult to do brute force, but I suppose if you were going to do something like that, I suppose you might do it's O of n for every single node, and then it would be times the number of connections that you would make, and that would be O of n as well. So a brute force solution might be O of n squared. It's a little bit, we're stretching it a little bit to get a brute force solution because there really isn't one. But that's probably where you could start. So step 3, identify the pattern. This sounds like a complicated problem, but when you actually read it very carefully, you'll see that it's pretty obvious what the solution is. So it's basically asking you that given 2 start nodes, your node 1 and your node 2, I forgot an E there, don't worry about it. It's then asking you, to find the distance to some node for these 2 start nodes, right? It wants you to find a node such that the maximum between their 2 distance is minimized. So in other words, for both node 1 and node 2, you need to know the distance to each node, right? More specifically, you're going to need to know the minimum distance to each node. And if you know anything about graphs, the simplest way to do that is a breadth first search, a BFS. And if you, but you're asking, okay, but how do we handle both starting nodes? Well, you're going to do a BFS for each starting node. So basically, all we really need to do is do these 2 BFSs, and we need to keep track of how long it takes to get from each starting node to each other node. And we can do that with a hash map, right? What we can do is we can keep track, say we start at node 2, we can keep a hash map that says what is the distance to 8? Well, that's going to be a 1. And then what's the distance to 1? Well, that's going to be a 2. And then what's the distance to 4? Well, that's going to be 3. And then if we look at starting at node 6, well, what's the distance to node 4? Well, that's going to be 1. And then what we can do is we can look and see that, well, we already reached node 4 from the first starting node. So if we look at the maximum between these 2 distances, it's 3. So our return is going to become 3. And then from node 4, we go to node 9, and we'll see that we can get there in 2. And then if we jump from node 9 to node 1, we'll see that we can get there in 3. But then again, we'll notice that we've already been to node 1 in the first BFS, and we'll see that the maximum between these 2 distances is 3. But then we'll also notice that the index is smaller than our first answer, which was node 4. So then we're going to replace our answer with node 4, we're going to replace our answer with node 1. And yeah, that's how we're going to solve it. So let's go on to code. Okay, so this is going to be a BFS. So we're definitely going to need a queue. And then also, as we said before, we need to keep track of how long it takes us to get to each node in each BFS. So we're also going to need a unordered map. If you're in Python, this is a dictionary, but it's pretty much the same solution no matter what. So the first thing we need to do is initialize the queue. So we'll just say that's the BFS. And since we're going to do the BFSs sequentially, we only need to have one of them. Then we need to have our 2 maps that we noted before. So they're going to map they're going to map a node index to the distance to get there. So we'll have node 1, and then we'll have M2. And since it's a BFS, we need to keep track of what nodes are in the queue, or we've already visited, so we don't double visit a node. And these maps are going to be a handy way to do that as well. Then we need our solution variables, right? So we're going to need both the smallest distance, so we're going to call that ret distance, and we're going to start that at int max, right? So we're looking for the minimum between two maximums, so we'll start that at int max, and then we need a variable to actually keep track of what the solution node is. So that's going to be ret node. And it starts at -1 because, as it said, if we can't find a solution, then we just return -1. Okay, so then with a BFS, let's start with our base case. So that's going to be node 1. Sorry, we called it BFS, right? And then we need to note that the distance to node 1 is 0. So that's our base case. So then let's start the breadth first search. So while the BFS is not empty, we will figure out where we are. So that's going to be the front. Sorry, I'm so used to just using queue. Just going to be the front of the queue. Okay, so then what do we need to check? Well, we first need to check to see if this node can actually go anywhere. So if edges of our current node does not equal -1, as the problem definition says, if we can't go anywhere, then it's going to be -1. So if it's not equal to -1, and we need to make sure that we haven't been there before, because there is cycles in these graphs. So that's going to be n1 find edges of cur equals m1.end. So that means if this node can go somewhere and we haven't already been there, then what we're going to do is visit it. So we're going to go, what we're going to go ahead and do is we're going to mark this down as visited by marking the distance it took to get there. So the distance, that's just going to be the distance it took to get to this node plus 1. Pretty simple. Then we're going to push it onto the queue. Okay, so that's our first BFS completed. So what do we need to do now? So that's our BFS from node 1. Now we need to make a BFS from node 0. So do the same thing. We're going to push node 2 into the BFS, which will now be empty because the while statement says while it's empty. And then the same thing, we're going to note that node 2, the distance to node 2 in this BFS is 0. All right. Is it not happy about node 2? Okay, no. All right. While the BFS is not empty, same thing. Get the current node. All right, so this is where it gets complicated. Now we need to see if we have a solution. So the first thing we need to do is check to see if we actually were able to arrive to this node from node 1, so the first BFS. So that's going to be the first map. If we can find the current node in the first hash map, the first BFS, then this is a potential solution. But it also needs to be a new minimum distance between the two, a new minimum maximum distance between how long it took to get here from node 1 and how long it took here to get from node 0. So that is the maximum between the distance it took to get here from node 1 and the maximum it took here to get here from node 2. If that is less than our current return value, then we found a new solution. So if that's the case, ret distance. If that's the case, then we can change the return distance to that. So just again, the maximum between these two distances. And then we also need to mark down the new node. So ret node just equals cur. But there's a problem here. Can you see if you can notice it? So the issue here is that you have to remember, if there are multiple answers, return the node with the smallest index, right? So that means we actually need to consider the situation where the maximum between M1 cur and M2 cur is actually equal to the return distance. So we can actually take care of that with a little fancy bit of conditional operators. So let's actually do that first. The new return node, what we actually need to check is if this distance is equal to the already return distance we have. So that's if this distance, this minimum maximum difference, is already equal to our return distance, then what do? Question mark. Well, if that's the case, then what we actually have to do is take the minimum between our current return node and our current node. Why? Well, because we want to take the minimum index if there's a tie. If that's not the case, then we can just take the current node as our solution, and that takes care of that little annoying caveat. All right, so now that finding the solution is taken care of, we can now continue with the BFS. So it's basically the same logic. In fact, if you want, and I will, I'm just going to copy and paste from above. So just change this to M2, this to M2, this to M2, and this to M2. So if there is an outgoing edge, so the outgoing edge is not equal to -1, and we have not been there before, then mark it down in the map, and then push it onto the BFS. So then once those two are done, we should have a solution. So let's go ahead and check that. And we do. There's obviously, you can do it a little more efficiently. You can also do it with a DFS, but in terms of runtime, this is going to be O of n, right? Because a BFS is just O of n for every node in the graph. You're going to visit it twice, once for each of the BFSs. And then the space complexity is also going to be n, because the BFS could fill up with every single node. So in terms of complexity, this is already the optimal solution. But if you want, you can look for tiny little improvements you can do. But that's the solution.